and we are recording. Basically, I don't know. All right, so last thing we need to talk about with this electrochemistry stuff is a little bit about concentration cells and then electrolytic cells. But something that they took off is this equation behind me called the Nernst equation. So here's what this is. I'll explain it, and then I'll tell you basically what you need to know. And we've already covered it.
Should we write it down?
No, you don't need to know it. It's not on the equation sheet. I just want to explain it a little bit. Basically, the E naught. What's that little naught stand for? Standard, right? Standard condition. So this you can get from the reduction potential sheets or any reduction potentials they give you, as long as you know the cathode and the anode. This E is at non-standard conditions. So if you look at page 829, it says the effective concentration on cell EMF, electromotive force. Again, that's just the voltage. And if you look up here, this natural log of Q, we've seen Q before. That's the initial concentration. So if you have your two beakers in your galvanic cell, you have an initial ion concentration in both of them. What happens is as it runs, it goes towards equilibrium, and when it reaches equilibrium, it stops. We talked about that before break, and that's kind of the driving force. It's thermodynamically favorable, right? Spontaneous. The batteries just work. They do that until these ions reach equilibrium, which will make the E equal to 0. So, and that's where Q is equal to K, and I'm kind of rambling a little bit, but I'm throwing out things that we've heard all along this year with equilibrium and reactions. So this is not anything you need to know, but what you do need to understand is that when these voltaic or galvanic cells are working, they're trying to get to equilibrium. And when they do that, it stops working. Like I said, we wrote that before break. We talked about it. You guys seem to understand that. So I'm not going to be giving you anything with this. Not for homework. Again, it won't be on the AP test because it's not on your reaction sheet. But I just wanted you to understand that when you change your standard conditions, the voltage will change too. And that's what this is all about, is if you change the concentration, you change the voltage. So what we wrote, I think we wrote before break, was the further from equilibrium, the greater your cell potential will be. Why does that make sense? The further the cell is from being at equilibrium, the more voltage it's going to produce. Why does that make sense?
More electrons to react.
Yeah, it has more electrons. It's further from equilibrium, so it has to react that much more to reach it. So kind of like we just showed on that practice problem we just did, is when you precipitated the Pb plus 2, the voltage went up because it reacted more. There's more reactions going on. The closer you are to equilibrium, the lower the voltage. That's the only thing you really need to understand with this. Okay? And this is, again, this is not really part of the curriculum anymore. But that the concentration can change. So I wanted you to just show you this quick. Flip to page 830. And you see that there's the equations there in the shaded area. And if you look at the middle of that page where it says E equals 1.1 volt minus 0.0257 divided by 2 times the natural log of Zn plus 2 over Zn plus 2 over Cu plus 2. Let's look underneath that. I just want to explain a little bit before we move on here. It says if the ratio of zinc to copper is less than 1, the natural log is a negative number. So that the second term on the right-hand side of the preceding equation, so in other words, this part of it, okay, will be positive. Under this condition, E is greater than the standard E naught. If the ratio is greater than 1, E is smaller than E naught. So that might be a little confusing to you. So again, all you really need to know is a general idea of what I'm talking about. When you change the concentrations inside the cells, it's going to change the voltage relative to E naught. That's all this equation is used for. They can't ask this. That's what they say in the AP Bible here. They can't ask you to use this, but I just want you to understand that if you start changing concentrations, you can change the voltage. And again, the further from equilibrium, so the greater the concentration ratio, think of it that way, the bigger the ratio difference, then you're going to have usually more voltage. The closer it is to the equilibrium ratio, less voltage. So it's a little confusing, I know, from your perspective, me just kind of talking about it, but I'm not going to, there used to be a lot I did with this. I'm just not going to do it because they took it off. Most things this year I taught it anyway, but we're kind of getting close here, so I'm not going to get into this if you don't need to use it. Let's see if concentration cells help you understand that a little bit. So go to page 833. A concentration cell says, because electrode potential depends on ion concentration, it is possible to construct a galvanic cell from two half cells composed of the same material but differing in ion concentration. Such a cell is called concentration. So let's just sketch one real quick here. So concentration cell. Concentration cell. So again, just draw two beakers. We'll put, I don't know, we'll use, let's see, what is this? We'll use the one in the book here. It uses zinc, right? So we'll have zinc here, Zn here, Zn here. We'll connect this with a salt fridge. I didn't leave myself enough room. Wire, voltmeter. There we go. Okay. So let's say this one, I guess, you know, I don't have a whole lot of notes on this. So we'll just use the book. What do they use? 0.1 and 1. So let's say this is 1 molar and this is 0.1 molar solution. That's what a concentration cell is when you have the same zinc and, let's say, zinc nitrate solution. I don't know if they even set it up there. It says zinc sulfate. So let's say in here you have Zn SO4, Zn SO4. This is 0.1, that's 1. That's called a concentration cell. This will still produce a potential, still will produce voltage because there's a difference in concentration. The more concentrated side, this side is where reduction takes place. The less concentrated is where oxidation takes place. It's good I drew it this way because usually I draw it the other way. Usually we always put our anode over here, cathode over here, but this one is flipped. I didn't think about it, just kind of drew it there. So this here is where you're going to have Zn plus 2 popping off, and electrons are going this way. And then here, your Zn plus 2 is going to be gaining electrons jumping on to your cathode then. So again, your anode's going to lose mass. This is going to be your cathode gaining mass. So why am I showing you this? What am I trying to get you to understand? That there's a different type of cell called concentration, where it's the same material, just different concentration. And because of that ratio I was just showing you with that Q, the ratio of the ions here, that will affect how it moves or how it reacts. So, or how it flows, the electrons flow. So the less concentrated solution is where your oxidation takes place. More concentration is where reduction, so your electrons will flow. In concentration cells, let's see what I wrote here. It said the direction of spontaneous electron flow can be determined by considering the direction needed to reach equilibrium. Right. So in general, to reach equilibrium, if this one is going to reach equilibrium with this one is going to what? What's going to happen to the concentration inside these two of the Zn plus 2 ions? Right, so what's going to happen here? Is the concentration of the Zn plus 2 going to go up or down as this runs? Up, because Zn plus 2 is going to increase and the Zn plus 2 is going to decrease here. So they're going to reach an equilibrium. So let's write that. Let's write that. This will run until equilibrium is established. Oops. Equilibrium is established. So this will run until equilibrium is established. The spontaneous flow of electrons, from 0.1 molar to 1.0 molar results in, I'm kind of running out of room here, results in Zn plus 2 concentration increasing in the oxidation half cell, I ran out of room. So I'm writing what I want to write here. Results in Zn plus 2 increase in the oxidation half cell. And then underneath it there, I'm going to keep writing, bless you, Zn plus 2 decreases in the reduction half cell. So that's what yes.
Are these very weak? Like,
Yeah, yes. They're not as strong as a regular galvanic cell. Yep, these are definitely weaker. I think it actually goes on to say that somewhere here.
What's something that would use a concentration cell, like in today's society?
I think you can make batteries out of the same material.
Which one's more efficient, concentration or galvanic?
Galvanic. But these actually, interestingly that you asked here, happen in our body. So they have a good example in the book, so we'll get to that in a second. What was I saying there? James asked me the question, they're weaker. Yeah, so the gist of these, and all you need to know is that these spontaneously, they're thermodynamically favorable because they want to reach equilibrium. So when you hook them up, based on the concentration difference, they're going to try and reach an equilibrium, and that's what happens. So electrons flow, increase the concentration Zn plus 2, decrease here, eventually they'll reach an equilibrium and they'll stop. So that was it for concentration cell. Now, if you look down at the bottom, it says a biological cell can be compared to a concentration cell for the purpose of membrane potential. Membrane potential is electrical potential that exists across the membrane of various kinds of cells, including muscle cells and nerve cells. It's responsible for the propagation of nerve impulses and heartbeat. Membrane potential is established whenever there are unequal concentrations of the same type of ion in the interior and exterior of the cell. For example, the concentration of K plus ions in the interior and exterior of a nerve cell are 415 respectively. Treating the situation as a concentration cell and applying Nernst's equation, which is what we just had up, for the one kind of ion, they show that the K plus is the external divided by K plus of the internal. And you can see that the E naught is set to 0 because that's when both are the same. Your E naught, when it has cathode minus anode, that's going to be 0 because it's the same exact reduction potential. So you're going to be subtracting from itself. Thus, the electrical potential of 84 millivolts exists across the membrane due to an unequal concentration of K plus ions. So how could you increase that voltage? Look at that example right there in 834. How could you make that 84 millivolts higher? Or lower? Either one. Andrew?
change the concentration.
Yeah, so you can make the 15 to 400 a larger ratio or a smaller ratio, right? And that's going to change your E. So that's why it's I think appropriate for me to mention and show you the equation, is that it's all about the concentrations that will change your voltage. That's the gist that I need you to understand, not the math. They took the math off. It's just understanding when you alter the concentrations, you alter the voltage. And then there's a whole bunch of stuff about batteries that we don't get into. We can talk after we're done with the test, but that's not on the test. Okay, I think we're good with that. Let me just double check, make sure. All right, now James' favorite thing to do. Electrolytic cells, or electrolysis. Here we go. Okay, so electrolysis. Keep the books. Electrolysis, electrolytic cells. And what is the difference between a galvanic and electrolytic? Well, let's see here. If you guys go to page 845, 844, 845. Yeah, good pictures on there. And then if you look at figure 18.18, down at the bottom left there, you can see that's what James likes to do. Hydrogen and oxygen gas. So this is where you are essentially running electricity through a solution or a molten substance. What's that mean, molten? Look, yeah, you melted salt, molten salt, or something like that. You can run electricity through it, and then at your anode and cathode, you will have reduction in oxidation, and you actually end up splitting or separating that substance. Now, it gets a little tricky If you're going to do this with a molten substance, it's way easier than in water. And we're going to explain that. I'm going to explain that right now. That's the goal today, to get through that. So let's look at figure 18.17. Let's just read about it a little bit here. Let's skip A for a second and just look at B. It's a little simpler. It says, a simplified diagram showing the electrode reactions during the electrolysis of molten NaCl. The battery is needed to drive the non-spontaneous reactions. So what we're going to write here, these are non-spontaneous. Oops. Well, what's another way to say that? Right, not thermodynamically favorable. Non-spontaneous, so not thermodynamically favorable. Right, so non-spontaneous. Therefore, it needs a power source, which is where the battery comes from. That's why the battery is there. It needs a power source. And essentially, when we say electrolysis, what we should think of is using electricity to perform a chemical reaction or a chemical change. Just say chemical change, which is a chemical reaction. That's what we're doing with electrolysis. And, you know, just to get an example here, splitting water, splitting H2O into H2 gas and O2 gas is pretty common. That's an example that you should at least, when you think electrolysis or electrolytic cells, that's something you should probably think of. But if you look at the picture there on 844, look at B. You see oxidation, you see reduction. It's the same, right? Stay with me, guys. Anox, red cat. So anode oxidized, reduction is at the cathode. So anox, red cat. So at the anode, you have your oxidation at the cathode. So in that picture on the right there, on B, you would have chlorine bubbles on the anode, and you would have solid sodium over on your cathode. That's what would be happening over there. Look on page 845. This is a diagram showing electrode reactions during the electrolysis of water. Note that the signs of the electrodes are opposite to those of a galvanic cell. Yeah, in a galvanic cell, anode's negative because it supplies electrons to the external circuit. In an electrolytic cell, the anode is positive because electrons are withdrawn from it by the battery. You don't need to know that. I just wanted to show you the picture of it. That's really why I'm showing you that. You do not, the book here specifically said in bold, students do not need to know the signs of the anode and cathode. It does not add to a deeper understanding of the material. I agree. I don't think it does either. Memorizing signs doesn't really do much. Understanding what's happening at the anode and cathode, that's the important part. So yeah, if you look at that, if you just dissolve some hydrochloric acid in water, it really helps the process. Why? If you want to send electricity through water, what's the problem?
Needs ions.
Yeah, water doesn't really conduct. Pure water doesn't really conduct, right? No ions. So you put acid in it to help conduct. Now, here's the interesting part. If you look at the oxidation and the reduction, it's two different reduction potentials there, two different half reactions. The one on the left, you have water losing 4 electrons and turning into oxygen gas and 4H plus ions. And then on the right, at reduction, you got 4H plus ions gaining 4 electrons and turning into hydrogen gas. So those two work together. And what I want to bring your attention is go to your reduction potential sheet. You guys still have those handy? Find, if you go down, I think 5 from the top, 1, 2, 3, 4, 5. Do you see that half reaction? O2 plus 4H plus 4E minus. That's the one half reaction occurring at your anode in that picture. Then if you keep going down, all the way, wait, where is it? Where is it?
It's like halfway down to 0.
Yeah, I'm looking for the. Yeah, okay, there it is. But you got 4H plus 4E negative. So there's the other one. There's your H2. So there's your two half reactions on there, and it's going to be important that you understand how to look at the reduction potentials because it dictates which one is going to be at the anode, which one's at the cathode. So kind of throwing a lot at you right now. But this is very different than galvanic. You need power because it's not spontaneous, right? Not thermodynamically favorable, and that's examples of electrolysis. So now what we'll do is get right into an example. Here we go. All right. So I think I'll start with something a little easier, then we'll do something a little harder. That seems to make more sense than the way I usually teach it. Let's go with, let's go with molten salt. So if we had molten salt, molten NaCl, in an electrolytic cell, we want to calculate the E naught. So, I guess we can kind of sketch this here. Just one example in our notes. So we have the here's your battery connected to this one here, and let's just say, for argument's sake, here's our anode, here's our cathode. Who remembers the ions? What ions? This is different, but this is just a review. In a galvanic cell, and in this one, but in a galvanic cell, where do the ions migrate? Who remembers? They go through the salt bridge, but where do the cations go? To the cathode, right. The anions go to the anode. Okay, keep that in mind here. So over here, what we're going to have happen is your Na plus is going to be jumping onto that. And then over here, your Cl minus is going to be gaining electrons from this electrode. So, I don't really know how to show that. I don't want to draw electrons, but that's what's going to happen over here. And then you're going to see bubbles around this thing. The bubbles are Cl2. So, here's how we do this. We want to calculate the E naught cell. How do we find that? What minus what? Cathode minus anode. Right. Let's go to our reduction potentials and look up the two half reactions. But we're supposed to figure out which one is the anode and which one's the cathode. This is why we're doing an easier one here first. So let's look them up. So let's find Na plus. Where is it? Na plus. Let's write them both down. So you have Na plus an electron yields Na, and the E naught is negative 2.71. Let's find the Cl minus. It's up top there. Cl2 plus 2 electrons. Cl2 plus 2 electrons yields 2 Cl minus. And that one is 1.36 volts. Does that make sense?
Because it's not thermodynamic.
Right, because it's getting power, right? So, we know that this one is going to be at the cathode, because I already showed you, and this one's going to be at the anode. So Andrew just said it's backwards. What does that mean, Andrew?
It means that the cathode is less than the anode.
The cathode is less than the anode, right.
Yeah.
So what did we say before? For galvanic, how did we phrase it before in the galvanic?
Oh, I don't know how to phrase it.
How did you understand it?
I always understood it because in the galvanic, whichever one was more positive was, whichever one was bigger was the cathode.
Okay, yeah. Well, all right. So if we look at the reactions there, or not the reactions, the reduction potentials there, your Na plus is down on the bottom and your Cl minus is up top, right? So what's actually happening inside this cell? What's actually happening?
It's losing energy.
Right, isn't this the one that they showed us here?
Yeah, it's in the top. So electrons from the battery would go to the Na, or the cathode.
So say that again?
The electrons from the battery would go to the cathode.
Right, so the Na plus is gaining, right? So let's make sure we're understanding here. This is our reduction because it's gaining electrons. What's happening to the Cl minus?
Electrons are being taken away.
Can everyone look at this and flip that in their brain and say, okay, because the electrons are here, this is gaining the electrons, this is really losing the electrons. So this is the part I'm concerned with. This is how I teach it every year. I say find the electrons and find the ions. What's happening in here? You have Na plus, Cl minus. The Na plus is gaining. That's reduction, that's your cathode. The Cl minus is losing electrons and becoming Cl2 gas. Why is it losing? Because it's on the other side of the arrow. Yeah, the arrow's going that way, that doesn't matter. If they're not on the same side, they're losing, right? So that's how I want you to think of it when you're looking at the standard reduction potentials, because what they'll do is they'll give you some options. You have to pick out the right one and what makes sense. So now this is losing electrons, this is gaining. So now, if I didn't tell you if I didn't tell you any of that, I would expect you to be able to figure that out. So what Andrew said helps. Oh, it's just reversed. Yes, that's one way to think of it. The other way to actually figure it out is understanding what's happening in the picture and then picking out the half cells that make sense. This is happening here. They're gaining. This is losing electrons, and the Cl2 bubbles are being formed. So that's how we can figure out this is oxidized. This is reduced. This is oxidized, and then the same thing, the same little trick, anox, red cat. So now that we know our voltages, how do we find the E cell? What do we subtract? What minus what? Negative 2.71 minus 1.36, and what do we get? Negative what? 4.1?
07.
07. Okay. All right, so that's exactly what's happening over here on page, I don't know if you put the books away, but page 844 in that top right. They already labeled it for us, but that's what's happening, yes.
So what does that number actually mean? Is that like the amount of volts you have to
Put into it, yep. That's the voltage.
Is that for 1 mole, technically?
Yes, that's for 1 mole.
I feel like it seems like, I know with water, it seems a lot more difficult than that. Like you have to put a lot more in.
Yeah, well, the water is more, this is, like I said, the molten ones are easier examples.
Yeah, no, I just meant like when you actually do the numbers, I don't think water would come out. It doesn't look like the numbers would have water come out so high for like a mole of water. There
Right, well,
gases either.
yeah, water's tricky, again, because it doesn't conduct very well. So, but anyways, yeah, that's how we would do a molten example. Now, let's do an example dissolved in water. So let's take a KBr solution. Focus. Calculate the E cell for a KBr solution. Here we go. KBr solution, right. I don't know if anyone noticed, but it's AP Agber now instead of AP Chem apparently.
Yeah, I saw that.
Everything is Agber now.
It's Regents Agber.
Alright, so if we have an electrolytic cell with potassium bromide solution, here's what I want you guys to do. I want you to understand there are 4 things happening inside this cell. 4 things. You have K plus ions, Br minus ions, and you have the water. All 4 reduction potentials are listed on this sheet. So there's four things happening. So here's what we're going to do. We're going to write the anode options over here and the cathode options over here. It'll make way more sense after we do the problem, but we'll just get through it. All right, so let's think about what's happening here. You've got KBr dissolved in water, so you have K pluses, Br minuses floating around. So K plus, is that a cation or anion? Good, cation. Br minus is an anion. Okay. Now, in general, the anions flow to the anode, which would mean it's... There's a reason that we learn everything in order here, so stay with me. The cation is K plus, the anion is Br minus. Anions flow to the anode, which means it is oxidized, anox. So the cations flow to the cathode, which means it's Reduced. So let's say that again. The anion flows to the anode, so it's oxidized. The cation flows to the cathode, so it's reduced. So the K plus should be getting reduced, and the Br minus should be oxidized. But it's not that easy. Here's what. Write this down. 2 Br minus equal Br2 plus 2 electrons. I think that's exactly, I think I'm reading them off of the, yeah. Alright, I'm writing it a little different than on your sheet. I'll explain why in a second. And then the other one is 2H2O yields O2 plus 4 H plus 4 electrons. So let me just get these down, then I'll explain. Cathode options, K plus 1 electron yields K, and then H2O plus 2 electrons yields H2 plus 2OH minus. Okay. Now all we have to do is look these up. I got these off of the reduction sheet. Again, with these electrolytic questions, I think the fact they don't give this to you in the test anymore limits the type of questions they're going to ask with this. So they're going to have to give you this information. Have to. I don't know any other way. There's no other way I could do it. If I couldn't do it, you can't do it, so they're going to have to give it to you. So I just don't understand why they took it off. It doesn't make any sense. But anyways, enough about that. Let's look up their voltage. What's the voltage for the Br minus? 1.07? 1.07 volts. What about the this one? 2H2O yields O2. I might have flipped that one. 1.23. All right, K plus. Negative 2.92. Negative 0.83 for this one right here. Okay. Here we go. I'm going to read what I have in my notes. Listen carefully. Clear your mind. Try and follow me. The more positive reduction potential, the better the cathode or reduction. The more negative the reduction potential, the better the anode or oxidation. Let me read that again. The more positive the reduction potential, the better the cathode or reduction. The more negative the reduction potential, the better the anode / oxidation. Now hold on one second. The reason I separated these and the reason I wrote them the way I did, because inside that electrolytic cell, you have K plus, Br minus. We know that K plus is a cation. What does that mean? Cathode. What does that mean? Reduce. We know this is going to lose electrons. That's why I said that's an option for my cathode. I know that's going to happen at the cathode because it's a cation. I know this is going to gain an electron because it's going to... Nope. Did I say that wrong? I said that wrong. I said it right, drew it wrong. The K plus is going to gain an electron. Br minus is going to lose an electron. I know that's going to happen because the anions get oxidized. That means lose electron. There's also water inside there. Water can do either or. It can lose electrons or it can gain electrons. So whenever you have a solution in an electrolytic cell, you always have to take water into account. That's why these problems are hard. If this was just molten potassium bromide, the H2Os would not be there. That would be your anode, that would be your cathode, subtract those, game over. Now you have to think about which one is going to win out. Which one's more reactive? Which one's going to react? Which one's going to react? I'll say it one more time. The more positive the reduction potential, the better the cathode or the reduction. The more negative the reduction potential, the better the anode or the oxidation. So Andrew, what are you going to say?
So you want your answer to be as close to 0 as possible?
You want your answer to be as close to 0 as possible.
Like with the value
Cathodes H2O and anodes 2Br.
So let's see. So the cathode, Greg, what were you saying?
Cathode should be
Yes, this is the one we're using for the cathode.
And BR always wins.
This is the one, right. So, again, the more positive the number, right, the more positive the reduction potential, that's the reduction. And then the more negative reduction potential, the better the anode or the oxidation.
Will the
So,
water always be one of the results? Like, will the water be the anode or the cathode?
well, what would make it not?
Well, I mean, like, say for example,
Pick one that would not be. That would make water not.
cobalt would not make water.
Where's cobalt?
Somewhere. It's like wait, negative 0.2.
Negative 0.28. So it's smaller than that number.
Yeah. So
That-
in
that
case
means-
the water would just kind of hang out and do nothing.
That right.
All right.
Yep.
So it's-
So this is what makes electrolytic cells tricky. So again, if you here's the most important thing that I get on you today, I hope, or you get from me, I should say, is not subtracting two numbers. That's easy. It's understanding what's happening in the beaker. These are losing electrons because that's what anions do. These are gaining electrons. That's what cations do. And then the water is given to you. One water is losing electrons, one water is gaining, and as long as you remember reductions at the cathode, oxidation at anode, you'll never get that messed up. This is losing, so it's over here. This is gaining, so it's over here. So when you clump them together with similar half reactions, then the next part is remembering which one do we take. Okay, so out of these two, right, the lower of the numbers, and then out of these two, you think, I guess, I don't know if you want to say bigger, lower, however your brain works there. I'll say lower of the number. So really it's the lower of the number for each one. But again, the way I wrote it, the more positive would be your cathode. That's more positive. This is more negative.
Closest to zero.
Or just the
Well-
one that's closest to zero.
Or I like how Andrew said that, closest to zero.
So in this one, will the cathode be bubbling and the anode have like a liquid bromine?
Yes, you would have liquid bromine oozing around, and then you would have hydrogen gas bubbling
That
at the
just
other.
doesn't sound safe.
Yes.
So if you think about it, you want it to be close to zero too, because it would mean it would be putting less energy into it.
Right. It would be closer to being thermodynamically favorable, because once it goes the other way, then it is.
Yeah.
But you can't do that with these. You
So
can't
you
do
want it
that.
to be as close as possible.
Yeah, I like that. It's close to zero, yeah.
So if you put like salt in there, it would create the oxygen in water.
Yeah, in fact, I did that example here. I was going to do salt, but I decided not to. Salt, you would get hydrogen and oxygen, yeah.
A minute there I was worried I'd recording gas.
So, yeah, remember I told you I couldn't remember off the top of
Yeah.
my head, so. All right, so how do we find the E cell? Now you did all that work, it's easy.
Subtract.
Cath minus anode.
So negative 0.83 minus 1.07. I don't think I actually,
Negative
Oh.
1.9.
I don't think I actually calculated it.
Negative 1.9.
1.9.
Is it negative?
Negative 1.9.
Yes. How come all our answers are negative now, but for galvanic cells they were positive? Right, so you have to give energy to this, so your E cell will be negative because it's not thermodynamically favorable, but the other one will be, galvanic will be positive. All right, let's try one here on your own before you get out here. Calculate, here we go, what am I doing? Electrolysis of silver fluoride, AgF, yes, AgF. You have a solution of silver fluoride in an acidic solution. It leads to the formation of silver metal and oxygen gas. I guess I'm being nice by giving you examples. So you have silver fluoride solution in an electrolytic cell. You run electricity through it, electrolysis, and it forms silver metal and oxygen gas. Two questions for you. First part, write the half reaction for each electrode. For the anode and cathode, write each half reaction. And then B, calculate the minimum EMF needed to operate this cell. What is that? That's the E cell. Calculate the minimum amount of voltage to operate the cell. That's your E naught. So give me the half reactions at each electrode and the voltage needed to run the cell. And then we'll go over that really fast, and then that'll be it. Dang it, ran out of time. All right, we'll pick up that tomorrow. I'm just going to give you a couple problems here. Chapter, where are we? 18, number 83. Number 83 and
83.
92. Chapter 83, or chapter 18, number 83 and 92. Because all the other fun stuff I had, we haven't learned yet. So we need one more day of new stuff tomorrow, and that'll be it. Yeah. We'll go over that problem. Finish that problem up too in your notes.